Hello, I'm Hugh Manfield and welcome to my science channel. Now today we're going to be talking about the expanding cosmos again because there's a few points that I didn't cover in my earlier video. And if you like my videos and you want to support the efforts that I'm making, you can always pick up a copy of my book Einstein and Aliens. And all of the topics that I cover in my videos are pretty much covered in the appendices and the science fiction story in the book. So, the Hubble model of expansion says that the galaxies are moving away from each other like raisins in a rising loaf of bread dough. Now, what does that mean? Well, if we took selected galaxies that marked out a cube, let's say there's a galaxy at each corner of the cube, over time, as the universe expands, that cube will expand and the volume inside of it will actually get bigger. There's more space being created somehow. Space is expanding, it's getting bigger. So when a light wave travels from a distant galaxy through this expanding space, it gets stretched and therefore it's redshifted. And this seems kind of plausible and everyone seems to be going along with it, but there's actually a few problems with it. And I'll explain what those are. We observe distant galaxies redshifted almost linearly with distance. They all follow along what's called the Hubble line. Now, this is an observation and it's been verified. Galaxies are redshifted. And we try to explain this with different theories, and the Hubble expansion theory is one explanation. And as I've shown in earlier videos, if space is expanding according to Hubble, and if it's a universal expansion, it should be happening everywhere. It should be happening between the galaxies, it should be happening within the galaxies, it should be happening within our solar system, and even in Brooklyn, where young Woody Allen can become depressed about the fact that the universe is expanding. And what would we see? If space is expanding within our solar system, it ought to slow the speed of an orbit. And if it's expanding within the galaxy, it would even be more powerful in slowing the speeds of orbits. So what do we actually observe? Well, within our solar system, and I've asked NASA about this, do they have to account for expansion of space when they chart the course of their space probes? And they say, no, all you need is Newton's law. Everything pretty much behaves according to Newton's law within the solar system. So there's no sign of having to deal with expansion, and maybe that's a sign that space isn't actually expanding within the solar system. So now let's turn to galaxies. The solar system is very small. You wouldn't even see it as a dot compared to the galaxy. So the galaxy is way bigger, so expansion of space at the Hubble rate is going to be a lot higher. And I've calculated that it's probably about 1,000 meters per second at the rim of a normal sized galaxy. And that's a lot because the force of gravity out there is very weak and an object will fall only a trillionth of that distance in the same time. So if expansion of space really affects an orbit, we ought to see the orbit slowing in galaxies. But what we actually observe is that the stars in galaxies orbit faster than predicted by Newton. And that might be a sign of contracting space. So when we observe galaxies, we don't see any evidence that space is actually expanding. So where else can we look? Well, the Sloan Digital Sky Survey has been mapping galaxies out as far as they can, and it's an ongoing process, and there's new surveys being done around the world, and we're constantly building a map of the distant galaxies. And what we see revealed in the map is that the galaxies form together into what's called the large-scale filament structure, and there's a set of voids and strings, and if you look at it, it's all pretty uniform. And it's kind of hard to tell, but it appears that the voids and the strings out here are in roughly the same proportion as the voids and the strings that we see closer in. Now this goes out to about 2.8 billion light years. So that's maybe a quarter or a fifth of the age of the cosmos. Maybe that's not far enough to see the difference. But what we should see, if Hubble expansion is going on, is that as the universe expands, the filament structure ought to expand with it, which means as we look back in time, we should see a smaller scale to the filament structure than we see in the present day. So here's a more distant, this blue area represents what's within this circle, and this goes out to about 6.5 billion light years. So that's about half the age of the universe. So at that time, the filament structure should be half the size that it is today. So when we look at filament structure in here, we should see filament structure out here roughly half the scale. But when we look at the Sloan data, it all still looks pretty uniform. We don't see a bunching up. And I've done a little slide to kind of show this. Here I've just taken a sponge with random holes and I've scaled it down for each billion years that would pass. So 1 billion, 2 billion, 3 billion, 4 billion, 5 billion, 6 billion. So at 6 billion years ago, it's going to be roughly half the size. And if you look at this cluster here, you can see this cluster is about half the size. So as you gaze across this collage of sponge images, you can see with the human eye, it can detect that the holes are getting smaller and closer together. And this is the effect we should see when we're looking out at the Sloan data. And when I plotted the Sloan data down here, it's really hard to tell, and maybe it's not conclusive, but really the human eye says that the Sloan data is pretty uniform. It's not becoming more and more compact with distance as we would expect. So where else can we look for evidence to argue for or against the Hubble expansion model? Well, there's also the anthropic principle. The anthropic principle says, why do we see the universe the way we see it? It's because if it was any different, we wouldn't be here to see it. And what that means in terms of an expanding universe is it would take a certain amount of time for intelligent observers to evolve. And let's say that's at this point here, indicated by the yellow plane. Anytime after that point, intelligent observers may come into being. And if we look at the expansion model, and especially the accelerating expansion model, it means all the galaxies are moving farther and farther apart. So as time goes by, as we look out into the cosmos, we're going to see fewer and fewer galaxies. And as the acceleration increases, galaxies are going to go beyond the Hubble horizon where we can no longer see them, and they will actually disappear from our observable sphere. And eventually, we'll be in an island galaxy all by itself, or maybe with a couple of other galaxies in a neighboring cluster. So the odds are, for an intelligent observer, sometime in the future, they would not see a galaxy-rich cosmos. They would see a cosmos devoid of galaxies. So the anthropic principle, the fact that we see a galaxy-rich cosmos, argues against the Hubble expansion model. The odds are that we shouldn't see a galaxy-rich cosmos if the Hubble expansion model is correct. So another place to look that argues against the Hubble expansion model. So when we look in the solar system, we see no effective expansion. When we look at the orbits of stars around galaxies, we see them orbiting faster than predicted by Newton, which would indicate contracting space, not expanding space. Once again, something that argues against Hubble expansion. The Sloan data appears to be uniform, which again argues against Hubble expansion model. And We see a galaxy-rich cosmos, and the anthropic principle argues against the Hubble expansion model because we see this galaxy-rich cosmos. So maybe there's a new model for the expansion, and I call it the falling vacuum energy cosmos, and I liken it to traveling on a space train. As passengers, if you're on a space train and it changes velocity, you don't see the change in length. An outside observer will see the train become length contracted and time dilated, but within the train, you don't see any of those effects happening. So the concept is that we are passengers in the cosmos. We can't have an outside view. Someone with an outside view would see space expanding as the vacuum energy drops. But since we're inside the cosmos, we can't have that view. So as the vacuum energy drops, space expands and becomes less time dilated, and yet we don't see the distance increasing. So if we had stars or galaxies on the corners of these cubes, as time goes by, the volume within that cube remains constant, not like the volume within the Hubble expansion cube, which increases over time. This volume remains constant, the distance between the galaxies remain constant, and this model exists in harmony with all the observations that I've gone through in this video. So based on the observations that we have, maybe it's time to consider a new model for cosmic expansion. And until next time, I'm Hugh Manfield.